Welcome. In the early 1600s, a French monk by the name of Marin Mersenne was playing around with perfect numbers, and I have a video on those. And he realized in that study the powers of 2 were important. So he actually played around with the powers of 2 for a while. That is all the numbers, doubling numbers from 1. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and so on. And in his playing, he discovered something interesting. If you subtract 1 from each of them, you'll get the numbers 1, 3, 7, 15, 31, 63, 127, 255, 511, 1023, etc. I guess I'm ignoring the first one because it's kind of trivial. But he looked at these and noticed that some of these numbers are prime. For example, 3 is prime. The second one in the list is prime. 7 is prime. The third one in the list is prime. 15 is not, but 31 is prime. The fifth one in the list. 127 is prime. The seventh one in the list. That 255 is not prime. 511 is not prime, I believe. That's 7 times 73. No, 7. Yeah, 73. There we go. That's not prime. 1023 is divided by 3. But he noticed that often when he played with this, prime numbers would appear in the list. So he actually thought this could be a good source for generating prime numbers. So he thought, okay, let's look at the powers of 2, subtract 1. Could they be a good way to generate primes? Not all the primes, obviously, but a good number of them. So primes that are of this form today, that we find today, are called Mersenne primes in his honor. So one thing I'd like to do is analyze this equation. When can a power of 2 minus 1 be prime? And it looks like from the data we've got so far that for 2 to the n minus 1 to be prime, it looks like we need n to be prime itself. So what I'd like to do is first of all prove, I guess the sort of contrapositive of that, if n is composite, if n factors, there's no way that this thing could be prime. That's what he's noticing, all these composite numbers here, 4, 6, 8, the ninth position, they all don't seem to be prime. Well, one thing about the powers of 2, they're particularly nice when written in base 2. For example, the number 255 is written in base 10. It's 2 times 100, 2 times 10 squared, plus 5 tens, 5 times 10 to the 1, plus 5 ones, 5 times 10 to the 0. That's an awkward way of writing a number if it's something to do with powers of 2. So look at the number like 32. That's really 16 plus 16, but I could write that second 16 as 8 plus 8. But I could write that second 8 as actually 4 plus 4, but I could write that 4 as 2 plus 2. I could write that final 2 as 1 plus 1. So actually 32 is 16 plus 8 plus 4 plus 2 plus 1 plus an extra 1. But let me bring that 1 over and write 32 minus 1 is actually the sum of the previous powers of 2. So if I were to write this in base 2, I've got 1, 2 to the 4th, 1, 2 to the cubed, 1, 2 to the squared, 1, 2 to the 1th, and 1, 2 to the 0. That's what it is in base 2, 1, 1, 1, 1, 1. In fact, 32 is 2 to the 5th, and I've actually got 5 ones. 2 to the 4th, 3rd, squared, 1th, and 0th. In fact, in general, 2 to the n minus 1 in base 2 is going to be the sum of the lower powers of 2, so in base 2 it just appears a whole bunch of 1s, and in fact it's going to be n of them. Well, now it's very easy to see that if n is composite, there's no way that this could be prime. For example, let me just make some space for myself. Let's do 2 to the 6 minus 1. That is going to be 6 ones when read in base 2. But if I do that, I can see 111, and I can see 111 appearing, which tells me this is 111 times something. In fact, maybe you want to fill out what the something is. Therefore, at the very least, I know that 111 is a factor of 2 to the 6 minus 1. That is 1 plus 2 plus 4, 7. This number is divisible by 7. There's no way it's prime. Or 2 to the 2 to the 12 minus 1. That's 12 ones. 2, 3, 4. So it's a bunch of groups of 4. That tells you right away that 1111 is a factor of this guy. This equals 111 times something. Exercise for you, figure out what the something is. Which tells you right away that 1 plus 2 plus 4 plus 8, 13 is a factor of 2 to the 12 minus 1. Alright, so clearly, if n is composite, I can pull out some group of ones that's corresponds to a factor of n and show this whole thing can't be prime. So the only way for 2 to the n minus 1 to be prime is if the index at the top itself is prime, just as the data is suggesting. Now, of course, this leads one to think that then, well, if the index is indeed prime, that must mean I'm generating a Mersenne prime. Well, unfortunately, that's not quite true. For example, if I just went one number longer in my list to 2 to the 11th and subtracted 1 from that, now that's going to be 2048 minus 1, 2047. Unfortunately, that is not prime. I believe that is 23 times 89. So it's not going to always give us a prime number. In fact, people today have only found 47 different examples of these Mersenne primes, and they don't know if the list should go on forever or not. I think most people would say the list probably does go on forever, but no one knows for sure, hasn't been proven. But, the nice thing about Mersenne primes, they're particularly amenable for analysis with computers, because computers like to do everything in base 2, and numbers that are nothing but a whole string of ones in base 2 are very easy to analyze. So when you read newspapers and found that a new prime has been discovered, usually the new prime that's been discovered is a Mersenne prime, because computers can handle them very well. So they're very handy objects. It's curious that only 47 are known. 100 years later, of course, the next natural question is to ask, well, what about a variation 2 to the n plus 1? Is that ever prime? And Fermat was the one to ask this. And he played with this, and he found 5 examples where this turns out to be prime. And every one of his examples, his circuitous connection, n has to be itself a power of 2. So you won't put in n equals 1, n equals 2, 4, 8, and 16. They all turn out to give you primes. So here's my next challenge for you. Can you prove that if n has an odd factor, different from 1, every number is 1 as a factor, there's no way then that 2 to the n plus 1 can be prime? So the only hope of 2 to the n plus 1 ever being prime is if n avoids having an odd factor. That is, n must be a power of 2. That's a good challenge. Go for it. Thanks very much.